in today's class, the main important thing what we are trying to understand to derive or try to develop the Dirac equation and its applications. So just to give an like you said, so just to give an introduction, uh, it is better to again start with the quantum mechanics because this is something we are mostly interested about the Dirac equation. But that is one like before to go into Dirac equation, probably as we already well educated about the quantum mechanics. So we first try to just mathematically try to understand why quantum mechanics, the non-relativistic quantum. When I talking quantum mechanics, mean non-relativistic quantum mechanics, where you consider the, like again so many times I repeat that when I say the non-relativistic quantum mechanics, that means particle velocity is less than speed of light. I mean, is comparatively very small compared to speed of light. So in non-relativistic quantum mechanics, where whenever we try to understand the quantum mechanics, one important thing is the wave function. So wave function is nothing but the state which described the time-dependent uh, phenomena of a given quantum given physical state, and one can able to understand or describe the system using the time dependent Schrodinger equation, which is known to us, like what the psi is the wave function, and it is just basically nothing but the energy conservation, like I mentioned here. So this you had the kinetic energy and potential energy, and then you get the total energy term. So this is one of the very fundamental concept in quantum mechanics. And where also the second important thing in non-relativistic quantum mechanics is the
Sorry,
yeah.
one question. So, like this quantity derivation is derived from Hamiltonian, right? So, the total energy is equal to kinetic energy plus potential energy, and then we use the Hamiltonian operator. Sorry, we
Yes.
use the momentum and energy operator to derive this quantity derivation.
Yes. So like here you had kinetic this is basically kinetic energy term. This is nothing but the, like if I just write down the momentum in terms of the operator where the p is I delta, then I can get the kinetic energy term and add the potential, which is nothing but the your Hamiltonian of a given system. Like we already discussed about Hamiltonian. And then if you are interested about the time dependent part of the Schrodinger equation, then you have the time evolution part. So where the phi is now function of space and time, because you need to do the derivative with respect to time and also with respect to space. So already in non-relativistic quantum mechanics, you got that idea to deal with the wave function, where you if you know the wave function, that means you had some idea of a given state, because the wave function is represent the given state. Now already you can see, just to remind you, the equation there is no H bar or no C, because as I always discussed several times, we are using the natural unit in high energy physics.
Oh, no, good question.
Yeah.
I understand the wave functions, like all those concepts that like mathematically I understand those,
Mm-hmm.
but in the physical reality, right?
Mm-hmm.
When we talk about a wave function of an electron, so wave function it represents a quantum state. For example, a wave like one example of a wave function would be like a cos I omega t plus phi, something like that.
Mm-hmm.
So that's like a plane wave,
Yeah.
and we can say like this plane wave is representing the electron in the ground state or free state, or electron at the high energy. So we can, like, for each state of the electron we can have like a separate wave function, and then we can use Schrodinger equation to solve the wave function.
Mm-hmm.
uh, I understand mathematically, but physically, how did we come up with the phi is equal to a cos omega t? Or is it like, okay, we are trying to see like, okay, like this is a differential equation, and what will be the common solution for differential equation? So, okay, a cos omega will be like the common solution for differential equation. Then we use this one as like an assign to electron. So, whether this chicken came first or it came first, that always like it's my in my doubt.
Yeah, I think in both are coming parallelly. I mean, if you are interested on making the biryani, I guess then it will be like in Calcutta biryani we had like chicken and egg together. But yeah, the concept of which one coming first is not coming, they coming together. Like if you consider a system where your wave function basically represent the given state. When I talking about the given state, that's some of the physical phenomena. Now, so like in this case, when I write down the Schrodinger equation, where I said is a time dependent Schrodinger equation. So it basically because and it is a second order equation, and which is kind of like planar equation. So whenever you want to represent a state where your wave function is a time dependent one, then your wave function it will be the one of the like easiest solution, the planar solution. Now the question is, why do you believe it is planar solution or not? You can just take an example of harmonic oscillator, because harmonic in quantum mechanics you can see in most of the cases they are talking about harmonic oscillator, and one of the main reason of harmonic oscillator is that this is a very fundamental one, as it is fundamental because if you see any kind of quantum state, you can replicate that using a harmonic oscillator problem. And automatically the solution of a harmonic oscillator is the sine and cosine, because that give you the harmonic oscillator problem. So, and now if I consider electron that is trapped in some potential, boundary potential, like when you solve the boundary value problem, and if you consider electron, if I try to understand the oscillation, one of the, and if I consider time dependent solution of the given problem, then one of the easiest choice is to uh, considering the sinusoidal function. Uh, so 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 now if I try to understand physically what that mean by the oscillator, the sinusoidal problem function, like one thing is usually all the physical problem, one can somehow try to solve it if you have an idea of harmonic oscillator problem. So that's why it's like one of the easiest solution one can think, but it's not always true. Suppose in your given system you have some perturbation, and that perturbation could affect your wave function. So mathematically, if I try to understand a given, suppose as I said, as you said, electron and the electron wave function, and then if it is a trap in some given potential, the easiest solution it's a sinusoidal problem.
Okay, okay, got you. Understood,
Yeah,
understood.
so that's why in quantum mechanics, like in Griffith books, whenever you can see, whenever they try to solve any problem, most of the problem it was somehow connected with the harmonic oscillator. And if
Okay,
you know the state, then you know how the time evolution happen with the operator. But suppose if I consider there is no time dependent part of the wave function, that means you just only go to a particular one of the state, so your state is not changed with time. So whenever we're talking about the wave function, that means we are interested on a given system, and first we try to understand in which state the system collapse. If it is time independent one, it doesn't depend on time, then the system will collapse in particular state. And then if you also try to if you are also interested how the state is evolved with time, then the sinusoidal concept in wave function come into picture.
got you. Thank you. One last question
Yeah.
before we move on.
You
So
can
we,
100 questions. Yeah.
so the wave function it applies only for quantum particles. There is no macro state. There is no wave function for a macro state. Of course, it can be derived, but it will be extremely complex. If I take there is no wave function for this book. Um,
Yeah, so whenever we say wave function is basically kind of to represent a given state. You can consider like now consider this is kind of like quantum mechanical. So in quantum mechanics, when you start the quantum mechanics, there's an assumption. So this wave function is one of the assumption of quantum mechanics. They assume that if you have a state, then you can represent that state using a wave function. Now, instead of wave function, you can just simply just consider a classical system, like classical harmonic oscillator. And now you want to understand how the system is evolved with time. And then in that cases, instead of considering wave function, you just define a variable. It, suppose you want to solve the two-dimensional harmonic oscillator. So you have two variables, x and y, and you want to see how x and y they change with time. So if you are in the classical system, you are interested on the variable and you are interested how the variable change with time. But when you come to the quantum mechanics, then we see instead of considering the variable, because in quantum mechanics, your variable became an operator. And to like in this case, like your momentum, time, so that's becoming operator in quantum mechanics. And then if you're interested in a given how the system is evolved with time, then we consider okay, the system is represented by a wave function, and that wave function is basically give you the idea or the concept how the state in which state the system collapse. And if you know that is a given wave function, and if you further interested how your state is evolved with time, then your wave function will be time dependent, and then you try to understand how the time dependent wave functions look like.
Got you. So basically, like the equivalent of variables in which is in the classical mechanics, in quantum mechanics is the operators. So an operator by itself does not have any value. So operator has to operate on something, and that something is the wave function that represents the state of the particle. So if a
Yes,
energy operator is operating on a wave function, that is which is the state of the particle, then we'll get the energy of the particle. The moment
yes.
operator operates on the wave function, then we get the momentum of the particle.
Mhm.
So that's how it goes actually. Okay,
Also,
okay.
just to add one point here, that suppose it's not like suppose you have a momentum operator. If I mean it's if your state is only momentum eigenstate, then your operator can operating on the given state, or you can do like you can do the Fourier transform like if you had a position eigenstate. So now here instead of talking about wave function, you talk about the state. So if suppose you have a position eigenstate and if you have momentum operator, then they can operate on that, but then you need to do some Fourier transform. So usually when a momentum operator operating in a momentum eigenstate, you get the momentum eigenvalue in the state bank. So sometimes the same thing we can define in terms of state, or you can say the same thing in terms of wave function. So wave function is just a representation of a given state. So if your wave function is a energy eigenstate, you're operating on the Hamiltonian, you get the energy eigenvalue and the state bank. If you're momentum operator, you're operating on the momentum eigenstate, you get the momentum eigenvalue and the momentum state bank. What that mean?
Right.
What that mean when I'm talking about the momentum eigenvalue? It means suppose you have a momentum eigenstate. Before operating the momentum eigen, sorry, before operating the momentum operator, you don't know in which state the system collapse because you had all possibilities. Now you have a momentum operator, you're operating on the momentum eigenstate, then your system is collapsed to a particular eigenstate, and you know the momentum eigenvalue. So you can measure the eigenvalue because whenever you're talking about the eigenvalue, something is measurable. So when your momentum operator operating on a momentum eigenstate, then you get some momentum operator, no, sorry, momentum eigenvalue, which you can measure. Same thing for the energy or same thing for any operator system.
Got you. So then, this makes one question actually.
Yeah.
So that, like you said, like there is like a energy eigenstate and then the momentum eigenstate, but all these we are always representing by phi, right? So psi over here, uh, psi
No.
phi. Sorry,
Yeah.
like this psi or phi.
It's up to you. I mean, you can represent your state by, and this is just your choice. Like here, whatever the notation I used, I can just simply say this is my. I mean, instead of considering phi, I can take psi, xi, eta, lambda, beta, gamma, whatever you want. But you have to declare. Like here, I said, what is the phi here? The phi is my eigenstate, or is one of the wave function. When I said wave function, it basically means that how the system is evolved with time. So when I said if it is my eigenstate, it could be alpha, beta, gamma, p. Instead of writing psi, I can write simply, can I write? Well, so instead of writing this one, so I can just simply write it. Wait, it's not working. Just give me a second. Okay, sorry. Where I'm going, not this one, this one. So instead of writing psi, I can just simply write with p. So I can say that p is my momentum operator, momentum eigenstate. So it's just a kind of notation. It does not matter. It doesn't
Okay.
matter. You have to take psi itself. You can take xi, phi, lambda, beta, gamma, alpha, delta. But what is important here? The most important message is suppose you want to operate a momentum operator, your eigenstate should be a momentum eigenstate. Or if it is not, then your one option is
Gotcha.
do the Fourier transform. Because by Fourier transform, you can change, suppose here a position eigenstate, You can do the Fourier transform of that state, and then you can get a momentum eigenstate. Then only you can apply a momentum eigenvalue, momentum operator, and then you will get the momentum eigenvalue. So you can represent whatever the way you want, but the standard notation is phi, which we represent in the wave function.
Gotcha. Thank you.
Okay, so what was this is the one. Now the next, so now we have some idea about the quantum mechanics, right? Now the question was, the next step was, okay, when we come to the regime of quantum in quantum mechanics plus relativity, so we make some connection between them, then we reach in the place of relativistic quantum theory. Then we already discussed is there is an energy momentum conservation equation. So if you consider only energy E equals to mc square, the well-known Einstein equation, but if you consider the energy momentum conservation in the relativistic quantum mechanical framework, then you can write down the equation. Sorry, this one. Then you can write down the equation with E square equals P square C square plus M square C to the power 4. But here I am just I am considering C equals to 1. So H and C, so this is my natural unit. So in this unit system, I can write E square minus P square equals to M square. Now this is just operator now. Now when so I can change this to operator. So I can now I just for simplification, I write down in terms of differential operator system, and this thing is operating on phi. So I can write down this thing in more better way. So I can write down this one, the whole, if I consider this is my operator. So this operator can operating on phi, where phi is my eigenstate. So the eigenstate psi or phi, whatever I consider, if I consider this one, this should be function of momentum and energy.
Exactly.
So when I consider this one, then I just operating on this state. So actually I am operating psi here. So when I operating this, then we already discussed, sorry, this this square will be not there, because this operator itself is del mu del nu. So whatever the equation we get here, this equation is known as the Klein-Gordon equation. So now, yeah. So what is the important message from this slide is that we already discussed this one, but I'm just trying to remind you. So when we are in the picture of quantum mechanics, non-relativistic quantum mechanics, we had Schrodinger equation where the state is represented by a wave function, and if we had a operator that operating on the given state, you get the eigenvalue and the operator back. That is my quantum mechanics. Now question is why we want to change from quantum mechanics to relativistic quantum mechanics, because we already know that there is a possibility of creating particle and antiparticle. Particle can generate, particle can annihilate, which answer the normal quantum mechanics or non-relativistic quantum mechanics cannot give the answer of why this particle create and generate. So we are interested in the relativistic quantum mechanics. Now in relativistic quantum mechanics, if we try to understand the equation of motion, then Klein-Gordon equation is one of the equation. It could explain some of the physical phenomena which Schrodinger equation cannot explain. Because what is important here in Klein-Gordon equation? In Klein-Gordon equation, we are in the relativistic domain. So energy and momentum is both are treating in the same footing. So now I'm in my case, in case of relativistic quantum mechanics, I cannot distinguish energy and momentum. And if this is the case, that actually leads me to the Klein-Gordon equation.
Okay, so the key important thing is like the energy and momentum should be in the same footing.
Yeah.
It's indistinguishable.
Yes. Sorry.
So energy and momentum same footing is like both are let's say E is equal to mc like it's not mc square. E is equal to mc square, but momentum is mc. Both are in the same footing.
So just to clarify you, I mean, when we discuss this one in relativity, I mean, in relativistic kinematics. So the one of the important thing relativistic kinematics when we discuss that, like, if I consider, if I just try to write down x mu, so we have the time and then we have the position, right?
Yeah, contravariant also.
Contravariant covariant. I mean, I always confuse with the which is contravariant covariant, but yeah.
Upstairs is contravariant.
Okay, so the important message here, whatever the x mu is represent, so in this case, both your time and position, they had the same value. You cannot say that time is different, position is different. They are treated in the same footing. The same thing, if I write, if you remember also we discuss about p mu, so we can take mine, so
E by
yeah,
C, P
yeah,
vector.
energy and momentum. So this mathematical representation is corresponding to the relativistic quantum mechanics. We already discussed in relativistic kinematics. Now, whenever we're in the relativistic kinematics or relativistic region, and also the if the consider particle size is very small, that means electron, proton, and they can move at very high velocity, then relativity and quantum mechanics they add together. So in relativistic quantum mechanics, which we further call it like quantum field theory, in relativistic quantum mechanics, we consider energy and momentum. You cannot distinguish between them. They are like they have some interrelation between them, but they are interconnected. You cannot separate them. So we call it in more physical the energy and momentum they're treated in the same footing. And then if we try to understand the dynamics, ultimately Schrodinger equation give you the dynamics of the particle in non-relativistic region, and the Klein-Gordon equation was one of the possibility to understand the dynamics of the particle, a small particle like electron, proton, muon in the relativistic region, where
Actually, the E square minus P square C square is like that is like it's elegant actually. The thing is like if I'm thinking physically, right, when the electron has some energy, an
Mhm.
electron moves, so there is some momentum, but the difference between the energy that it has and the momentum that is showing, that difference is exhibited as mass. So that is like somewhat elegant, like if I think physically.
Yeah, because ultimately, like usually we know this one E equals to mc square. So this is well known. Like energy can convert to mass, mass can convert to energy, and but the also one more important thing here. This is in the case when the particle is at rest. In this case, P equals to 0. So if your particle is at rest, that time energy and mass they can change with each other. Energy can convert to mass, mass can convert to energy. But the question is what happen when the momentum is not 0 and it's not very small, is something really important one. then then the in this case your momentum is always 0. That's P equals to the rest mass. That's, you remember, we consider this energy as a rest mass energy. But when your P is not 0 and P is well in a large enough, then your energy and momentum, that is whenever any particle gets some energy, that energy comes from two sources. One, because of the particle rest mass, and second thing, because the particle is moving. So the total energy, it is one part coming because of the its rest mass, because if it's a massive particle, it has some rest mass, and also if it is moving, because of the kinetic energy. So it gets some energy from the kinetic energy, and so you can think in this way that this is total energy. So this is your total energy. This is due to kinetic energy. This is potential energy. I mean, not really true, but you can just
Gotcha, gotcha. It's kind of thinking, yeah, think along
yeah,
this line.
yeah. So the important message from this slide is now we are in the domain of quantum mechanics plus relativity. So we try to understand step by step what
One question,
yeah,
Haradhan. Sorry to
yeah,
interrupt you.
yeah, no, no.
This Glenn-Gordon equation seems extremely simple, right? Like the derivation seems extremely simple. Like I mean, where I'm going with this, like I'm just going back to like 1926 when Glenn-Gordon was thinking about this equation. So it like all he has is like, okay, I have a Schrodinger equation. I have like a rest mass energy equation, E is equal to mc square. Now I know something about relativity. So how do I combine? Like, and then they just did some small algebra, and then they got this new equation that has like that has a profound impact. So I think what I'm trying to say is like two things. One thing is like all the derivation that I've seen so far, Klein-Gordon equation or even Dirac equation. Dirac equation, maybe some mathematical, there is some abracadabra there, but at least in Klein-Gordon, it's quite simple actually. So, and after Klein-Gordon and Dirac, is there any new equation that we like simply we did some abracadabra, small abracadabra, then we got some new equation, and then we got like okay, now we are explaining some new things like quantum gravity, something like that. Is
Yeah,
it happening now?
yeah, there are thousands of such equations. I mean, yeah, I mean now, I mean almost every day there's new and new theoretical paper come out. So there's thousand of them. This is second answer. The first answer about the simplicity, because this is not that simple what we are thinking right now. Because if we just go back to that era, the first thing what they need to know about this, how the energy and momentum they are interconnected. So the concept of, first of all, okay, the concept where to reach to the relativistic quantum domain, it was not very easy to understand, first of all, because that was a time when quantum mechanics itself was like CQ1 is, I mean, there's a very famous lecture by one of the guy from MIT. It I think is available on YouTube. He said, if anyone claimed that he understood or he know quantum mechanics, either he is lying or he don't understand anything. Because even there's so many things, so many puzzles in quantum mechanics still exist, which is very difficult to understand. So even so that time when the quantum mechanics itself was not very clear to everyone, and then Einstein came up with this relativistic special theory relativity or general theory relativity. So and they tried to merge with them. So this the concept of merging was the most difficult one. I mean, you can just simply come up with some idea, but you also need to think in terms of reality. Like in reality, then when the electron, proton, those particles are discovered, then this concept was more accepted because the particle when they discover the electron, they are moving with very high speed. They are very small nanoparticle. So, then the concept of quantum mechanics was first accepted, and then they try to understand further. Then okay, if the particle, the electron, the motion of electron, one can describe in terms of electron, then what will be happening? The particle is moving very fast, very high velocity. So the relativity come into picture. So this mathematical derivation is very simplest one, but the concept was difficult. And first of all,
I understood.
they need to accept that. That was a difficult.
Understood. Understood. Hey, one thing, like if we solve Schrodinger equation, what do we get? We get, let's say that we are applying Schrodinger equation on a wave function that is represented response of electron. So if we solve Schrodinger equation, we get the plane wave equation. That's what we get. That explains that explains that explains the flow of electron. That explains the push. Like that explains how the electron looks like. Is that correct? Like if we solve Schrodinger equation, we will get this. What do
Yeah.
we get if we solve the Glenn-Gordon equation?
So, if you remember, I gave you one problem which you did not solve it. But just to understand, like if you know quantum, if you know
Sorry about that.
yeah, no, I'm just joking. So if you know Schrodinger equation, and if you try to solve the Schrodinger equation, the wave function, whatever you get, that wave function give you the idea of how your state is collapsed in particular given state, right? But what is the constant there? The constant was that the system you are looking into, it's a non-relativistic system. So that is Schrodinger equation is perfectly, I mean, it can give you all the information you want to know if you are in the non-relativistic domain. Now the question is what we can understand from the Klein-Gordon equation. So the Klein-Gordon equation can give you the idea of any particle. Let consider particle, which is the velocity very high speed, tiny particle, so that we can make engagement between quantum mechanics and relativity. So they come together, and then if you try to understand what is the dynamics, so ultimately whatever the solution of this Klein-Gordon equation, the phi or psi, whatever you consider, that will give you the idea about how the dynamics of a given system happen, where your energy and momentum, you cannot distinguish them because they come together because of the relativity itself. So if what we can understand from Schrodinger, that is the next slide what I have. So let's consider I have the Schrodinger Klein-Gordon equation. So I write it in terms of our interesting notation mu nu. So I just write down the Schrodinger equation here. It's not a Klein-Gordon equation. So from this point, we are in the domain of relativity and quantum mechanics. So for a moment, I forgot about non-relativistic case. Now, what is the important thing here? So one of the important thing in quantum mechanics also to understand the equation of continuity. What that means is, suppose you have some particle is moving. If you know the energy density, then you are interested how the energy flux happen. So the energy density, energy flux, that merge together, and then you get something called equation of continuity. It is also come from the general physics. So, and that equation of continuity give you the idea of flux, how the system moving, how the system is evolve with time. Now, this Klein-Gordon equation also is pretty good enough to explain this flux of motions in relativistic domain also. So just to give the full picture, so I write down the Klein-Gordon equation, and this Klein-Gordon, I consider this whatever the phi or psi, this is one of the solution of Klein-Gordon equation. Then I am interested to derive the probability density function, or you can say the density function. So to do that, the same thing also do in quantum mechanics also. In Griffith book, they did have a full derivation in terms of Schrodinger equation. So like this equation, I just multiply with I psi star. This is because I can multiply anything because this is identity one. So I just multiply this one, and then whatever the equation I have, whatever the phi and psi, this phi is not only real, it could be complex also, because the final solution is e to the power exponential 1. So this phi has a real part and also has some imaginary part. So it's a complex number. Or this is basically whatever the phi or psi, it is a element in the Hilbert space. So you had all possibility of real and imaginary one. So I take this complex conjugate of the given state, multiply with imaginary number, and then multiply this Klein-Gordon equation. This is step one. The next step, I take the complex conjugate of the Klein-Gordon equation and then multiply with minus I psi. This is the same thing what we also do in quantum mechanics. In Griffith book, you can find out. Then if we just simply subtract this equation 2, the equation I defined here, and equation 3, then I can get something which is similar to the equation of continuity. What is the equation of continuity in general mechanics or something? So you have some, so what is the rho? Rho is we call this probability density. And what is the J is called probability current. So you have some flux which is changed with time, and that you can incorporate with how the density is changed with time. So if I just try to do some mathematical abracadabra, then I can find out what is the probability density I can get from the Klein-Gordon equation. So I can get the probability density and probability current density also. Then
Okay.
then what is the important thing here? What is the main conclusion from this Klein-Gordon equation is why we started the Dirac equation, because this just to give an introduction why you need the Dirac equation. So now let's consider whatever the Klein-Gordon equation I have, this Klein-Gordon equation I have, I consider what are the wave function. Let's consider this is one of the solution uh, of free particle. So here I consider particle which does not have not bounded. It is free particle. It can freely move it with some energy and momentum. So then I can write down my wave function as some normalization constant. We're not interested about normalization constant right now at this moment, but I just consider defined in terms of n. So this n is a normalization constant or kind of like amplitude, and I had some uh, time part and momentum part. So this is just a simple solution, time-dependent Schrodinger equation solution. But in this case, I am not in the non-relativistic domain, I am in the relativistic domain. So this phi is a solution for the Klein-Gordon equation. And now the question is, if I go back, so this is what I get from this equation. I just compare this equation with this one. I know what is my probability density. And if I just simply put this phi into this equation, then I'll get something. Just you can just do this is your homework, next homework, just to complete this this calculation. If you put this everything in this equation, just take the first order derivative, complex conjugate here and there, then you can find out what is the probability density, which is usually, we know probability is from 0 to 1, that is always positive. But whatever we get something 2e times n square. So this is always positive because it's square of something, we always positive. But if your energy is negative, then your probability density will be always negative, because this is a number. This can't be negative or positive. This will be always your positive because this is square of something. It will always positive. But if your what is the probability density? It is proportional to the energy of a given particle.
Yes.
Now the question is, now as I already mentioned, now we are in the domain of relativistic quantum mechanics. Now your energy, there are two possible solutions of this. If I just take the square root of this, there is positive and negative. So if your energy is negative from the Klein-Gordon equation, where you get the probability density,
density is also negative.
That will be negative
because number is 2 and then the n square, so that cannot be negative.
This is always positive. This is always positive. 2 is always 2. I mean, this can be something negative, but if your energy is negative, your probability density, that will also be negative. What that interpret, that is one of the drawback of Klein-Gordon equation. So what we learn apart from this mathematical juggling, what we learn that if we are in the non-relativistic quantum mechanics, then Schrodinger equation is a solution. And if we do the same thing, Schrodinger equation, you can see your phi will always positive, not phi, rho, which is probability density. If you do the calculation, it will be always positive, because in non-relativistic domain, your energy is, there is no negative solution of the energy. E equals to mc square. There is no negative solution. In non-relativistic domain, we don't write like E square equals to m square c to the power 4. We write always E equals to mc square. So that is a like only solution, E is positive. And if we just do the same calculation in Schrodinger equation, you can always find out this rho, the probability density, what I write here, this thing will be also always positive in a Schrodinger equation, but in Klein-Gordon equation, this could be negative.
Yes, exactly.
So that is not possible. I mean, that's one of the drawback of the Klein-Gordon equation. But
yes, probability is always from 0 to 1. There's a negative probability.
Yeah. So, but what this Klein-Gordon equation can do, apart from this problem, suppose you have a potential, one particle is there which is moving very high speed energy, you can get the state. You can get what the energy eigenstate, you can get the momentum eigenstate. Those things is perfectly doing, but it has drawback. The energy density and probability density, it could be negative. So this is
that is the reason.
That is one of the drawback where Dirac was so pissed off. He's like, this is not possible. I mean, obviously he find out the solution later when he tried to derive the equation by himself. So this is one of the reason why this negative. I mean, there is more other reason. I'm just trying to make it like simplified one. There are many other reasons, but one of the reason was that negative probability density. That's why I just mentioned here some others. So this is, I'll come back to later. What is the other one where Dirac interested to do that one? So Dirac tried to derive, and he tried to think instead of considering this way, what could be a possible way one can get the equation of motion where the energy density will be positive, not energy density, momentum density will be positive.
Gotcha. Actually, this one reason, the other reason that I was like I read about was basically the Schrodinger equation time derivative is one time, so single order, one order, but here the Klein Gordon the time derivative is like two orders,
Yeah.
second order, and Paul Dirac didn't like it actually. So that was the
Yes.
other reason that he thought,
Yes.
okay,
Yes.
try to
Yes.
see how can I make it like a single order.
Yes.
But this the explanation that you give that makes sense actually. Probability density cannot be negative,
Yeah,
so
it's
that means
supposed
it
to.
is
This
breaking
is
the rule.
this is actually one of the main reasons why because this is something cannot. I mean, okay, other thing he does not like it or not, that is his personal problem, but that is not the physics. But the main physics was the probability density cannot be negative
Yeah, agreed,
because it should be
agreed, agreed.
positive. So then what he tried to do, he tried to think how one can factorize the energy momentum relationship. So so is it clear till now up to this point what it is? Because up now
Oh yeah,
we
it's very clear.
yeah,
It's
now
very clear.
we are going to do more mathematical juggling because we need some more mathematical concepts. Okay.
No, it's very clear.
Okay.
Yeah, why you are going from
Yeah.
Glen Gordon to Derek?
Okay. So now what we will do, what not we, but what did I try to understand, how one can factorize the energy momentum relationship. So okay, this is already we know square equals to p square. This is Einstein. I mean Einstein is given. Then also he write down the p mu. Oh, sorry, I think I mixed up this plus minus sign here, but okay, doesn't matter. But what we import, we are needed here this inner product between two momentum operator. So if we just try to do this inner product of p mu, if I just remind you, if I just try to get it p mu with p mu, you will I should get some p mu with p mu, then you will get e square minus p square,
His case is P square.
right? So this is exactly what we get, e square minus p square here, and minus m square. So instead of writing this one, so we can also write down this is already we are interested, because this is if I just try to remind you from where we were in the Dirac equation, Klein-Gordon equation, we will start from the same places. So we start e square minus p square minus m square, then operating on the state given psi or phi, then we can get the Klein-Gordon equation. Now here, again, we are going to start from the same places, but we are trying to do it other way around. Now what Dirac tried to do, this p mu p mu, he tried to factorize it. This p mu what is something like a square minus b square formula. Not really, but I'm just trying to make analogy, because this is a inner product of two four vector, so like a square minus b square. So we know we can write down this as a plus b, a plus b
Into A minus B.
into a minus b. Okay, let me remove this one, which is not really true, but I just try to make analogy. So I can get something which is like a plus and minus. Now I am going back to some more mathematical notation.
No, hold on. It's not exactly A plus B, A minus B. So we have like a P upstairs mu, P
Yeah,
downstairs mu. That is changed to
yeah. This is the next thing what I'm trying to say. But in this case, you have the four vector, right? You have four vector here, inner product of two four vector. So I mean, what is? Let me just remove all these things. Okay, so if you have like a square minus b square, so this is a two dimensional, one dimensional, so basically one dimensional. So you can write a plus b into a minus b. So this is scalar quantity, right? A and b are scalar quantity here. So you need something which, because ultimately this b is fine. This b is nothing but m here. So this is your b, this is your b. B is fine. So you need to find out something what is a. So H is scalar quantity. So you need something which is scalar quantity, but what Dirac tried to define the scalar quantity in terms of inner product, because this is ultimately whatever this thing, this is scalar quantity mu minus b mu, p mu minus p mu, because you have 2 4 vector, but when you do the inner product, you get something which is like a scalar product, scalar quantity, right? So he tried to define what is A in this format. So what he did, he just simply do the inner product between two quantity. What is the P? P is my momentum, the operator. P is a momentum, but he needs something, some constant or something which we have 4 vector, because now our space is not one, two dimensional, 4 dimensional, because you had energy and momentum. So he just defined something B and gamma. And if it is a 4 vector, then you can do the inner product between them. And inner product of 2 vector, it will give some number. So then you can make an analogy. What is this A and B I'm talking about?
Gotcha. So,
Okay.
okay.
So what is the K here? K and lambda. This is a kind of dummy index. So I did not give the sum. I use the concept of Einstein summation convention. So actually your K and lambda, there will be summation. I mean K equals 0, 1, 2, 3. But I'm following the Einstein convention. So I did not use any summation notation. There should be like one summation here with K, one summation here with lambda. But I don't want to make something complicated. I just assume that when there is some running index or dummy index or running index, then you can just consider that there is a K equals to 0, 1, 2, 3, lambda equals to 0, 1, 2, 3. Is it clear to now?
Yeah, it is.
Okay. So now let me go to the next one. So now what we are trying to do. So this is I'm trying to make it more simplified. I mean, probably in some of the book is that there are some more not more abstract way of do the calculation to derive the Dirac equation. This is for me. It is one of the simplest way when I try to think how try to interpret how the equation come into picture. Then I just simply do the multiplication. So in a naive way, I just do the like 1 by 1 multiplication, and then what is the K lambda beta gamma, that is K equals to 0, 1, 2, 3, lambda equals to 0, 1, 2, 3. So I just simply expand those up. So first one is 0, 1, 2, 3. I just simply expand those.
Okay.
And this one is supposed to be equals to P mu minus M. This is where we started. This is where we started. So whatever this quantity, if I expand this quantity, just doing some algebra, then I get something P mu. Now, if just look into this formula, we are interested something with P mu. Now look into here. One of the easiest way to get rid of these other terms, like that's because we need something we had something here, this quantity, and so I need m square because this m square is here. I need this quantity here now, but still I have this is one term and this is another term. So this term is not in this equation, right? This term is not in this equation. These two linear term. So one of the
So basically, we should get like a 16 terms in total, like a left hand. So beta k pk plus m, gamma lambda p lambda minus m. So since the k and lambda are like k0, 1, 2, 3, so total like 4 terms plus 4 terms. So it's like 16 terms we should get.
yes. But what I am interested, but if I just look into my equation, the final equation, what I am trying to get, P mu minus, there is no linear term. There is no single linear term. But if I just write down in this way, if I just try to multiply with them, I get this form. But here I had some linear term in momentum, right?
Yes.
But in my final equation or final form, there is no linear term. There is one inner product and m square. So I
Correct.
need to cancel this term, this and this one. I have to cancel this term and this term. So this is one positive term and this is negative term. Let me just clear once again. So this is positive, this is negative. So if I want to cancel them, one of the easiest possibility for me to consider the beta k and gamma lambda, beta
Both
k
are
equals to
equal.
gamma k. So then I can easily ignore
Cancel.
the linear term. So if it is if it is understandable till now, considering this, if I just come back once again this equation, so what is the beta k? This beta k I can write in terms of gamma k. So now what I am interested, so this is just mathematical, but I'm just trying to follow with the calculation because at least it's good to know how the derivations come out because no one use it further when they do, but at least it's good to know at least for one. So this is the one what we are interested. We start from here and considering this beta k equals to gamma k, in the previous equation, we get some term which are quite similar to this one. Then I was interested to write down the full term because this k and lambda, they are running index from 0 to 0, 1 to 3, and for lambda also 0, 1 to 3. I just simply expand this one. It's not needed, but I'm just trying to interested. But what is important here, if I just simply expand this term, there are many terms are come up. Now here, what is new thing came to picture is this gamma. So now there is even a special theory, it's called gamma matrix theory. So this gamma is already known that time. This gamma matrix was already known this time.
So what is the theory?
It's called gamma matrix theory. It's gamma.
Gamma matrix.
Yeah.
Okay, gamma.
So whatever the gamma, because you can see automatically, though we are trying to play with this one, we trying to expand, this quantity, not trying to expand, but we're trying to factorize the energy momentum relationship. And then we can get something beta here, some gamma here. And then just for simplification, we assume that beta k equals to gamma k. So now here automatically, though it was coming on the way, some of the constants, so we got some 4 vector here, and this 4 vector is nothing but some matrix, and we define this as gamma matrix. Now here, if I just simply expand this this term in putting 0, 1 to 3, I could get some of the relation here. This gamma 0 square for gamma 0 equals gamma equals to 1. If I put both k and lambda equals to 0, I get p0 square and gamma 0 square. Same, I get all these terms one by one. Why it is important? Why I'm going to do on this way? Because ultimately what I'm interested this p mu minus m square. This is what we are interested about. If I just simply expand this one, I get p0 square, p1 square, p2 square, because this is the inner product, right? Minus m square. So here, whatever the gamma, whatever this quantity, this. So this is coming from this gamma algebra or gamma matrix algebra, where this gamma 0 square, this quantity, this supposed to be 1 because I need p0 square because there is one gamma square. Just what we needed, we need only p0 square. So whatever the gamma matrix come to the picture, this gamma 0 square equals to 1. So this automatic, it's not assumption, this automatically come to picture. Gamma 0 square equals to 1, and all the other quantity, gamma 1, gamma 2, gamma 3, those should be minus 1 because that's what I needed, because there's a minus sign here. There is a minus sign here. To get that minus sign, this gamma 1 square, gamma 2 square, gamma 3 square, this should be minus 1. And also I had many cross product here. All this cross product. And this actually follows some of this because I don't need all this cross product, because in my final form, this P0 square, P1 square, there is no cross product. There is no P1, P2. There is no P2, P3. So all the
But
other, sorry.
one question. So this gamma 1 square, the next slide, gamma
Next
1
slide.
square plus equal to gamma 2 square equal to gamma 3 square is equal to minus 1. So how can a quantity can be minus 1?
No, this is
The
actually
square of a quantity can be minus 1.
this is not actually not a number now. Actually, already I told you that gamma is a
That becomes
matrix.
like a matrix.
This is a
Okay,
matrix.
okay.
So this is a
So
mat.
it's
This
basically like
is
it's
actually
like a
like
cross product,
minus
product product.
1, 0, 0, 0, or yeah, something like this, depending on the matrix how it will be. So this
Okay,
is
okay.
like, as you said, the cross product of two matrices could be negative one. So just following this equation, so this all gamma 0 is supposed to be. Why it is important? It will come in later in many different cases. Actually, this is from where actually the concept of gamma matrix was very important in physics later. Yeah, so this is 1, this is minus 1, and all the other first term, if I try to combine and write in our favorite notation, mu nu, in covariant quantavariant form, this is supposed to be 0. If your mu and nu equals to, if your mu and nu they are equal, then it will be 1. If it is not, it will be 0. Because yeah, so if it is, wait once again. So yeah, so we try to define a kind of general form relationship between the gamma matrix or gamma matrix. So mu nu is, we use a kind of plus minus. So if you just remember in quantum mechanics, we use x and p, we call it commutation relation, where this is x minus p minus x in quantum mechanics,
Gotcha.
right? But here
Gotcha.
we have some plus notation here, which we represent with this second bracket. It's called anti-commutator relationship. So what are the gamma matrix we define in the algebra? This gamma 0 square, that is equals to 1, and all other gamma matrix 1, 2, 3, that is minus 1, and they had some anti-commutator relationship between them. So we are not interested with all other gamma, because there are many gammas you can define, but we are interested on those gamma matrix. We'll come to our Dirac equation, where they have to obey this relationship. There is an anti-commutation relationship where this equals to 2 g mu nu. This g mu nu is our and the well-known matrix is g1 0 0 0 0 minus 1 0 and 0 0 minus 1 0 0 minus
We
1.
saw we saw the matrix in a
Yeah,
Lorentz
yeah.
transformation.
This is the exact. This is not Lorentz transformation, but we call this what is called. I forgot the name. Sorry. Metric actually.
Yeah, in the Griffith book it was there
Yeah,
actually.
I
Dirac,
forgot. I forgot the name exactly. It's called something metric. Sorry, I forgot the name. It's called Minkowski. It's called Minkowski.
Minkowski matrix. Yeah, yeah,
Minkowski
yeah, correct,
matrix.
correct.
So now you can understand what is gamma. This gamma is nothing but matrix. So because they always, so we are interested only on those gamma matrix which are obeying this equation or this relation, this anti-commutator relation.
So what are we doing in the left hand term? Bracket gamma mu,
So
gamma
let me
nu.
which term, this term.
The first one, bracket. Yeah, that exactly. What is it like? How do you like? What is it? What a cross product or what is it?
No, this is what we came back from here. So when you had this, from where we come to this picture. So see, this is the first we define this gamma 0 square, gamma 1 square, gamma 2. We know what is here. It's 1. The first one is
Yeah.
1. This is minus 1. This we know. But you can see there is other cross product here. I mean, gamma 0, gamma 1 plus gamma 1, gamma 0. So you can see just from where I get, I just simply expand this term. if we expand this one, you can get, just do some mathematical abracadabra. You can find out a lot of terms. I just trying to arrange all terms in a proper way. So when I consider P0, P1, one of the term coming from here, like just see, if I put gamma k equals to 0, so I guess gamma 0, P0. Lambda equals to 1, so I get gamma 0, lambda 1 plus lambda 1, gamma 0, and then product of them. So I have some many cross product here. Now, if we see all of the cross product is just mu nu plus nu mu, right?
Yeah, correct.
Yeah. So
Can you go to the next page? Can you go to the
yeah,
next slide?
uh,
So here the last term, right?
yeah, this last
Uh,
term.
so the last term, my question is like, what is this notation?
It's called
How do you?
it is called anti-commutator relationship. I mean, when you use this third bracket, we call commutation. The momentum and position that commute each other, and this is anti-commute. So when you have minus sign, so we call this the momentum and position, they are commute with each other. If it is zero,
Okay,
if it is in this case, if it is plus, we use the notation called anti-commutation relationship.
okay.
Okay, so this is about, so we are interested on those gamma matrix now forever. I mean, this thing will become almost every time. So this algebra is very important. And also we probably not now, but we'll need another matrix, gamma matrix, which is called gamma 5 matrix. This gamma 5 is defined in such a way that it's a product of gamma 0, gamma 1, gamma 2, gamma 3 with some imaginary number. Why we need this one? Because this is a picture where the gamma matrix come into more details. So whatever the gamma 5 is defined, it is defined in this way because we need some unit matrix from the gamma matrix. So if I define in this way, the ultimate, if I take square of this one, I get 1. This is how the gamma matrix was defined. And if I take uh, anti-commutation relationship between gamma 5 and gamma, any of the gamma matrix, it will be always 0. And also those are like Hermitian matrix. So gamma 0 is Hermitian matrix, and also gamma 5 is Hermitian matrix. Hermitian means the complex conjugate of a given matrix. If it is same to the matrix, then it's called Hermitian matrix. And
Okay.
but this gamma matrix itself is anti-Hermitian matrix, because if you take the Hermitian conjugate of this one, you get the minus of mu. This gamma 0 is a commutation matrix, but not gamma mu 1. So gamma mu is a anti-Hermitian matrix. So this is some algebra, probably when you go through further, it will automatically come into picture. So you don't need to remember anything, but because it will come
Gotcha.
into picture later, but just to complete the story. Okay, so what we gain from this all mathematical algebra till now? So what we started, what we are interested? We are interested to define an equation of motion in relativistic quantum mechanics, where our main idea to get the positive probability density function. So to do that, what we do, till now what we did in the mathematical calculation, we start with the energy momentum relation using our 4-vector notation. Then we try to factorize that. So we define in terms of 2 factor. This is like a plus b, this is a minus b. Okay, and we use instead of using just simple a plus b, we define the a using inner product of momentum with some gamma matrix, and b is our m. Okay,
Okay.
now so what we get till now? So now, so this will be operating on some given state psi. So there will be also one psi here. Okay, and this will be so this will be supposed to be 0, because this will be the equation, right? So there's two possibility of this solution. Either you can consider this is equals to 0, like if your a plus b times a
Trivial
minus b
solution.
equals to 0. So you can take a plus b equals to 0 or a minus b equals to 0. So you can take any one of them equals to 0.
Agreed.
So conventionally, we take the minus 1 is equals to 0. So if I just once again go back, so we take this quantity equals to 0. The product of two number, if it is 0, then one of them should be 0. If both of them 0, that means trivial. That means 0 times 0 is always 0. So something 5 times 0 is also 0. So we take this quantity is positive 1. So take it as a number, but something minus m, we take conventionally, it is equals to, you can take the other one also 0, doesn't matter. Now, what is this P? P is our momentum operator in 4-vector notation.
Yeah.
So I just convert this one. P equals to, I just put this P in a momentum
Different
operator
derivation.
notation. And this gamma one is, I just to, because I need something to make a like near product. So I just use a contraction of mu. So instead of lambda, I just change it to mu because it's my running index. I can change whatever I want. So whatever the equation I get, this is the equation which is known as the Dirac equation. Now, what is the important thing here? What is the gamma matrix? We define gamma is it's a first of all, it's a matrix, and it is 4 by 4. It could be we call it a column matrix. Like whatever the gamma, it's a basically kind of a column matrix. We'll define
Okay.
later what is a gamma matrix and how they look like. And but what are the important thing here? Initially, in quantum mechanics, what is the wave function? It's just represent your state. But here in Dirac equation, the wave function is not only a kind of observable, not always something, but it's a kind of it has a matrix representation. Even in quantum mechanics also, wave function has a matrix representation. We know. But what is the difference here? What are the wave function psi? We call is not only a single matrix, not a simple matrix, which is called bispinor. I mean, it has some 4 by 4 representation because we had some 4-vector relationship here. Okay.
Okay. Okay.
Okay.
Okay.
So what we get till now, we get what we aim for. We want to define the Dirac equations. So this is the equation I define here. What we just do get from some mathematical algebra. We call it as a Dirac equation.
Gotcha.
So
So
is it
I
clear
gamma
till now?
mu d mu minus m psi is equal to
Yeah.
0. Yeah, it's clear. Clear.
Okay.
I need to look into the algebra a bit more,
Yeah.
but
Yeah. So I think I already sent you the notes. So
yeah, yeah.
you have the notes. Okay. So till now, what we learned that we are in the domain of relativistic quantum mechanics, and we are trying to understand, or we are interested to know about the dynamics of of a given system, where the quantum mechanics and relativity both are important. So then we try to understand, trying to get a alternative solution to understand the dynamics of where the probability density function should be positive, because the Klein-Gordon equation had this drawback. So we do some mathematical calculation, mathematical abracadabra, then we find out, we reach up to certain point where we define the equation, which we call this as a, from now we call it a Dirac equation. Now question is, what is this psi? Uh, now the psi is, first of all, it is a metric. Now question is what kind of matrix it is. That means like here in this case, as it is equation, that means each and everything should be similar quantity. Like you cannot compare with apple with pineapple. So if you want to compare something, they should be same. So here, what are now we try to understand what is the psi itself. Now that means we need to know what is this gamma matrix. So we can consider any kind of 4 by 4 matrix that could be a gamma matrix, but these two guy, is called Broken and Drell. They had some convention. It's called Broken convention. They said, okay, we can consider any kind of metric, 4 by 4 metric, but this should be follow this algebra. One of this, there should be this should be anti-commutative relationship between them. And also this gamma 0 square should be 1, and gamma 1, 2, 3 square equals to -1. So keeping that in mind, so we are not interested at this moment with the gamma 5, so we are interested with the gamma matrix. So keeping that in mind, what they suggest that, okay, there is a possibility that we can think in terms of there is some called Pauli spin matrix. So we can define some Pauli spin matrix that could actually give you the hint what it is phi. And so here from this point of view, now if I consider a spinner, so this is the point where this concept of spinner come into picture. Because whatever the possible solution of this is, they come a conclusion from there that, okay, we can consider Pauli spin matrix. So we are interested in the fermions basically. Okay, so whatever the psi, it should be a possibility of a spinner.
Sorry.
Yeah.
So the polyspin matrix, I understood up to the point like the work and drill. He said like the gamma should have this convention, it should have this properties. So all those things are fine. But
Mhm.
where does this XX, SY, SC is coming from?
Okay, so what we are interested here, we are interested to define. I'll come to this picture later, but let me just to answer your question. We want to interested to know what is the psi, so what is the wave function itself here, and then we can we'll come to this later, but we can interpret this. Ultimately, the possible solution, one of the possible solution, it could be we can define the psi in terms of spinner. Spinner is basically spin matrix. So, and I think Pauli, before this one, Pauli already introduced the spin matrix for different orientation of the spin. So which is defined in terms of Sx, Sy, and Sz because of three possibility of spin coordinate system. And where the spin matrix is could be real, like here when I consider 0 is basically a 0. So we need some matrix which is 0 by 4 by 4 matrix. So if I try to expand this matrix, it should be look like this. So first we have some 4 0 here. One is 1 0 0 1, and this one is 1 0 0 1. This 0 is 0 0 0 0. Oh, sorry. So this is, so what we interested? We interested to find some of the matrices because we obviously we need to go with this physics, right? So we already the dynamics of spin was known that time for the fermions. So we need some 4 by 4 matrix. Like as I mentioned here, we need some 4 by 4 matrix, but this 4 by 4 matrix would be something like spinner, because this when you define the spin matrix, that is also like 0 1 1 0, but it's actually 0 is a 4 by 2 by 2 0 matrix, null matrix. One is 1 0 0 1 identity matrix, 1 0 0 1 0 0 1. So this is just his suggestion. Their suggestion that, okay, this could be, we can define the possible matrix which can follow the gamma matrix or the wave function. It could follow the Pauli spin matrix.
Okay, so what you're saying is like we want to find the gamma. We want to find the wave function phi.
Yeah.
So and then the phi uh, has to be fit in this equation. Like since the gamma has like a 4 by 4, so the phi has to become 4 by 4, and this could be one of the matrix.
Yeah, this is that's just the suggestion. This is their convention.
Gotcha.
They said, okay, we'll come back to later when we try to define exactly what is a phi and psi, or what is a phi, and then we can see this is actually something called this phi. We can define this phi in some xi, and we define something later. Xi or notation I use usually xi and phi. It's called, one is called psi and phi, not psi and phi. One is called xi and what is eta probably. Yeah, we can define. So what is this one? It is basically represent, this is a spin up matrix, this is spin down matrix. We'll come to this to later when you're trying to interpret the phi itself. So ultimately, will we reach to the place where the phi will be represent the spin dynamics. So this is just their convention or kind of like a suggestion that, okay, we can think in terms of Pauli spin matrix, and why it is needed, we'll come to in a moment. Okay, but we did not get the proper answer till now, because whatever main thing what we're trying to get, we are mostly interested with the probability density. We wanted to get the positive probability density, because that's why Dirac was, that was one of the reason why Dirac was pissed off by Klingon equation. So now we got the Dirac equation. So one thing what we try to understand, let's see either from the Dirac equation, the probability density, it is positive or negative. If it is negative, then there is no point to do all the mathematical calculations. So we need to reach up to a certain point where the probability density should be positive. So to do that, sorry.
No, I agree. Yeah, probability density should be positive.
Yeah.
That's the whole point.
So to do that, again, we do the same thing, same mathematical equation. So first, for like, if I just go back once again, I just expand this gamma mu nu. So it's like 0.
Four vector notation.
Yeah. So for sorry, there should be a minus sign here. This is not positive. This is not plus, but there should be minus sign. This, because the zeroth component will be positive, and this will be this, and this will be negative. I'll correct it later. So because this is a, like, if you remember, a mu with b mu, it will be a0 b0 minus a dot b. So there should be one minus sign, not plus sign. Okay. And then because we already discussed that gamma 0 is a Hermitian matrix, and also the phi, that is a kind of complex. We already know that from the quantum mechanics, the phi is a state of a Hilbert space, so it should be complex conjugate. It's a complex number. And then this is just we try to get the complex conjugate of the given equation. That's what I did in the next step. And then what we just in next slide, I'm trying to understand one by one component. So just I trying to get the complex conjugate of this one. Let's check what is this complex conjugate of this first term of this equation. So just for my own satisfaction, I just trying to expand this one. Like, what is gamma 0? Gamma 0, we know the gamma 0 matrix. This is itself is defined already, the gamma 0 matrix. And also whatever the psi 1, the psi is now also kind of like 1 by 4, is kind of 1 by 4 matrix. I just simply expand it and try to do some mathematical calculation. And I'm not sorry. What is the final message from here? If you just simply sorry. Yeah. So if you just simply do this this calculation by yourself on hand, is basically this quantity is a nothing but a complex conjugate. So this is Hermitian one. This one itself is Hermitian, but just product of them, as their matrix. So the product is important. So we get A B complex conjugate. The product of two matrix is complex conjugate. It will be B dagger, A dagger. And if your A and B is Hermitian matrix, then ultimately you get BA. So the product of this one is exactly follow this relation. And already I define this gamma 0 is also Hermitian matrix. Why I need this one? What I'm trying to do? I'm trying to define the probability density. So I was trying to calculate this quantity. So I trying to calculate the complex conjugate of the Dirac equation. So in Dirac equation, there's two forms. One is called complex conjugate of Dirac equation, normal Dirac equation. Okay, so just this, if I do this mathematical calculation little bit, I'm just skipping this one to give you the final conclusion what I'm trying to do. You can just
So quick question.
Yeah.
Quick question. So gamma d5 by dt, those are just multiplication, right?
Yeah.
So
So it is not
d5 by dt
it is not normal multiplication. It is a matrix multiplication.
Yeah, correct,
Yeah.
correct.
Yeah.
But okay. If it is matrix multiplication, is it commutative? D5 by dt gamma, is that commutative?
D5 by
dt, the first term over here. The first term over here.
No,
Here we have
this
d5
is
dagger
no, this is not a this is just simply like this is not
multiplication.
commutation. This is not commutation relation. I just want to what I want to calculate. I want to calculate the first term. So we had this quantity
No,
with
no. What
dagger.
I'm saying is like, see, in this quantity, right?
Mm-hmm.
If you go to previous slide,
Yeah. Previous slide.
yeah, previous slide.
This one.
So the no, the next, the
Sorry.
previous one.
Yeah.
Yeah, yeah. So here, the first, this non-complex conjugate. Uh, here the first term is gamma 0
Mm-hmm.
d5 by dt,
Mm-hmm.
or dou phi by dt, gamma 0 dou phi by dt.
Mm-hmm.
Once you take complex conjugate, just stay here. Once you take complex conjugate, the first term becomes I dou phi dagger by dou t gamma 0.
Mm-hmm.
So what I'm asking is like gamma 0 dou phi by dt or dou phi dagger d by dt gamma 0, both are same, right? In the sense like there is no, if I write gamma 0 dou phi by dt or dou phi by dt gamma 0, both are same, right? It's just
No,
multiplication. Okay, I know it's
that's what I want to check actually.
exactly,
That is
that's
what I want to,
exactly
because this is if it is that's because obviously I was a interested to mathematical either it is true or not. So just to do that, I just take this complex conjugate. Then obviously if I know my gamma matrix is a Hermitian conjugate. That's the way I define a matrix. Or this is a known one. That's this is Hermitian conjugate. But the wave function is not. So that's why there is one side dagger is there. So this is that's why I wanted to check mathematically there. It is either true or not. Okay. So what I'm inter because probably you can just later as the time constant. So what I'm interested, uh, let me show you the important thing what I'm interested. Yeah. So if you just follow this mathematical calculation, because if I going through this one, then I don't give you the final message what I want to give you. So if you just do the calculation, just following this set of slides, then I can define what is my probability density I can get from Dirac equation. And then I can find out ultimately, if I just do some more mathematical calculation, I can see the probability density, which is side Hermitian conjugate of psi and psi. So this is it's a product of inner product of two complex, two matrix. Like uh, you have one matrix A, B with AB. If you did this one, you always get a positive number. There's no possibility to get a negative number. So so this is one of the main message from the Dirac equation for today's class, that probably you just need to do this calculation once by your hand. I had the full derivation here, but the important message is that if we do this mathematical calculation in more deeper way, then we can see from the Dirac equation the probability density, what we are interested in Clapeyron equation also, which was negative there, we get something which is psi dagger psi. And this can't be negative. This should be this supposed to be positive, because you are taking the matrix multiplication of two row matrix with the column matrix, because that's Hermitian conjugate itself. So so the main message here, that if you consider the Dirac equation in the relativistic quantum mechanics domain, then your probability density should be positive. That one of the main message what we can get from the Dirac equation. Now the uh, question is what why it is important. The important thing is come a bit later when we talk about the Feynman diagrams, and by knowing this what is called the probability 4 vector, yeah, energy density 4 vector J mu, we can actually get the information when two electrons or when two electrons they interact with each other at the interaction point, whatever the interaction strength, that actually we can derive from here. What we'll do later bit. So if you consider the electromagnetic interaction, if we know the Dirac equation we can exactly calculate what will be the interaction length or interaction strength when two electrons they are interacted by the electromagnetic interaction. Yeah, so yeah, this part will go later about the application. So and in the next in the next class, I'm going to show you in where we can use the Dirac equation. I'm going to show you two applications. In one of the cases,
Okay.
in one of the cases, the moment when the particle is at rest, a particle it consider that's the simplest one. Then you can get more understanding what's the Dirac equation itself. So if the particle is at rest, so we consider the momentum equals to 0. Then we try to understand what is the solution, and then actually we can get the concept of what is this the wave function itself. If I consider this, I go to two cases. In one case, momentum is at rest, that's so p equals to 0. And the second case, when the particle is in motion, it has a momentum. Then actually we find out, then we'll show in details actually what is this wave function. Then we find out that wave function is nothing but a spinor. It is we mathematically show it. That will be one of the solution. And when we try to solve it, when we define the wave function, then actually we get four solutions. Like here in this slide I'm showing, this is here one of the wave function. The way I represent using some different notice I will discuss later, but we can find out two solution, possible solution. One of the solution is for we define for the positive energy with a spinor. Another solution could be set of solution could be for the negative energy solution. And we will define this one. We'll try to interpret this using the concept of negative energy, which nothing but the representation of a particle which is traveling backward in time. And when you take the positive one, that represent the particle moving in the forward in time. That has actually lead us to understand the Feynman diagram. And this is actually is called Feynman and Stackelberg interpretation, because they later give the interpretation with the help of Dirac equation. And that actually give us the more important information about the particle and antiparticle. So why Dirac equation is so important? Because we are in the domains of relativistic quantum mechanics. There is a possibility of creating particle antiparticle. So Dirac basically give you the idea mathematically, that how one can interpret the antiparticle or the negative energy. And Dirac was trying to give that possible interpretation of negative energy using the concept of antiparticle. And then later Feynman and Stackelberg, they tried to mathematically give the interpretation of this negative energy using the Feynman diagram. So this is the thing what I'm going to do in the next class. And there's also one more thing. When I'm talking about the particle and antiparticle, then automatically the concept of spin come into picture. Like in quantum mechanics also you have the concept of spin. In quantum mechanics, spin is nothing but a kind of inherent property. It's something it's difficult to sometimes someone says rotation with that, but that is not possible to interpret in that way. But when you come to the relativistic quantum mechanics in the particle physics domain, where the quantum mechanics and relativity come together, then the concept of antiparticle come into picture. And when you consider antiparticle, so automatically the spin come into picture, because that's how we can distinguish between two. So when we try to define the Dirac eigenstate, or what are the wave functions we define, automatically there's two spinor will become. One is a spinor for spin up particle, one for spin down particle. So that's why it's so interesting, because first of all, it give
Got you.
answer for some of the physical thing which is already observed, and mathematically also is very, very interesting.
Got you. Got you. Got you.
Okay,
Oh,
so I'll give you two homework. So one of the homework is to complete abracadabra. What is that one? Not this one. Because one thing I just skipped here when I do this, so just to for a one do this calculation in hand. It is very easy one, just to get this idea of how we define the rho and j, probability density and probability current density, and
okay.
just put
Slide
this,
number.
take this psi and just to put it here. Obviously, it's well, it's C. It should be supposed to be this one. This is the one thing, and the second thing, I discuss this one. Discuss this one. I discussed this one. One thing, yeah. Just follow this note. I think I try to make it right away. Just try to discuss this one. Just take this slide. This slide number 22. Just for your own satisfaction, just if possible, do the calculation one by your hand. To let you know how you define this probability. Because I'm just telling, I just skip some of the slide. I just showing you what is the probability density. And
So like I should start from slide 22 to derive
yeah,
slide 24.
yeah. So you start with 22. Start from here because this is a
Yeah.
slide I skip. So you start from here
Mhm.
and go up to just try to understand if you understand up to 26
6.
or
Okay.
27.
Okay,
Then
gotcha.
in the next class, I am discuss about the application because that is the more important one because mathematical derived Dirac equation is not interesting. The main interesting when
Yeah.
you're trying to use the equation,
How to
try to solve
interpret?
some problem, how to interpret some of the physical process.
Exactly, exactly. I agree with you.
Yeah.
Yeah, this is quite interesting. I mean, initially when I saw the Dirac equation, at least the Klein-Gordon equation, Dirac equation giving negative energy, I heard about this again science fiction, the warp drive and those kind of concepts.
Mm-hmm.
The warp drive, in Star Trek they use this warp drive, right? I heard about that. I mean, like people are trying to create warp drive, and when they try to create warp drive, they get stuck by need for negative energy.
Yes.
So then I thought, okay, maybe this Dirac equation might be some solution to the warp drive. So anyway, I was
Yeah.
just thinking like if you're familiar with that kind of concept,
Mm-hmm.
the
Yeah,
warp
this
drive
is
concept.
what we're going to show in the next class in when trying to solve problem automatically the negative energy because till now we don't see the negative energy itself yet because we're
Yeah,
just trying to derive a Dirac equation. So this is what we are interested at the beginning to just so today class we just try to see this Dirac equation. Then now when you do the some of the application like if a concept particle is moving in the relativistic quantum mechanical domain, then automatically the one of the solution will come with a negative energy solution. And then we try to interpret that using this concept of negative energy and antiparticle.
gotcha. Perfect.
Okay. So, any question till now?
Nothing for the moment. I think
Okay.
I think there are some what do you call I took some preparation for the class. That's why it was easy to follow.
Yeah.
Actually,
Yeah. Exactly.
that's why it
That's
was.
why I sent the slides in earlier. And
Yeah,
also, if you have any suggestion, I mean, if I go too fast, that's also you can let me know. I mean, if something is not really understood, so we can again repeat in the next class.
yeah, no problem. I think this is very clear. I think once we go to apply, I'll do this derivation and then I'll be preparing the application so the next class will be much easier for you.
Okay. Great.
Perfect. Hey, one last thing. I think we could have done 10 classes, right? I didn't keep count. We would have done 10 classes. So again, I will make payment for the next. I think we'll do like 8 classes because it starts from month, right? Month to month we can make the payment, so it'll be easier to track and stuff like missing out. So
Yeah, probably I also don't remember which class it is going on now, but
yeah, yeah.
yeah,
I think it will be 10 plus will be
yeah,
done. So
yeah.
we
We can.
can
Mhm,
we can assume like for April we'll make payment for the 8 class, and then May will make payment for 8 class. Like that we can
mhm,
go like that. So eight eight
mhm,
eight times. So I think it covers per month easily.
mhm. Okay, great. And also, if anyone else is interested to join, like in future, so you are feel free to invite
Sure.
on your behalf. I mean, suppose someone wants to join with you, so I have no problem if someone else is there with you.
Okay.
So you can feel free to invite anyone.
Yeah, definitely.
Okay,
Okay.
great.
Thank you.
Okay,
See you on
so
Sunday
we
then.
are meeting on Sunday, right?
We are meeting on Sunday.
Okay,
Sunday
great.
3 o'clock,
Oh,
3 p.m. your time.
okay, perfect. Okay. See you next
Okay.
Sunday.
See you. Bye.
Bye.